Part 2 of the Ocean Universe Theory. In this part of the Ocean Universe Theory presentation, we will offer a basic understanding of general and special relativity and its history. We will expose the experimental flaw in measuring the speed of light, and begin our discussions on how the relationship between matter and energy impact the fabric of the universe. To better understand relativity, we need to know a little bit more about its history. The concepts of the relationship between energy, light, and matter began to be established before Einstein expanded and encoded them into his theory of relativity. The relationship between matter and energy was identified by Samuel Tolver Preston in 1875, and it was mathematically stated by Orlando de Pretto in 1903. 2 years before Einstein stated it as E equals mc squared in his paper of 1905. According to Preston, if matter was subdivided into energy particles, these particles would move at the speed of light, and 1 grain of matter would be equal to thousands of millions of foot-tons. Michelson and Morley confirmed the consistent speed of light in 1887, while they were trying to measure Earth's movements through the ether, or fabric of space as we call it today. By the time Einstein released his special theory of relativity in 1905, the existence of energy and matter in the universe, as described by his formula E equals mc squared, was a well-established and accepted principle of modern physics. By the time Einstein was writing what was to become his theory of special relativity, the question of the existence of an ether had already become a highly charged issue in physics. While Michelson and Morley actually were trying to measure the speed of Earth's movements through the ether, they reached an entirely unanticipated conclusion. When Michelson and Morley could not measure the speed of the Earth through the ether using light, the conclusion that resulted was that there could not be an ether. Of course, the one thing that had not been recognized at the time was the fatal flaw in what we would call today the design of experiment process they employed. As we will see later, it is in fact that the speed of light was constant throughout the experiment that should have verified the existence of the fabric of space, or ether, rather than suggest that it didn't exist. The fatal flaw in their experiment was of course their mistaken direct use of light as the measuring stick by which to measure the speed of light, a flaw we will describe in detail later. However, it has to be recognized that if their experiment was flawed, then all the conclusions arising from it must be set aside, and any fundamental belief of cosmology and physics based on it must also be set aside to be revalidated. In essence, we must relook at our modern physics as if the experiment they made had never taken place. By the end of the second decade of the 20th century, the world had changed dramatically, and so had modern physics. Einstein had completed and published his second important paper, introducing the concepts of general relativity, which focus on the behavior of the gravitational force. The world had witnessed its first great war of modern times, and people stood in awe of the great military technologies that had shaken not only the land, but the very fabric of society as well. It was before this backdrop of rapid changes in technology and science, to which the great minds of science were trying to adapt their new theories into older, established postulates of the previous era, many of which had taken on the effect of natural law. One of these older postulates that plagued Einstein was the set of equations known as the Fitzgerald-Lorentz transformations, which had been defined to mathematically state a solution to the baffling outcome of the Michelson and Morley experiment to measure absolute speeds through ether, or the fabric of space. While special relativity proposed a model that operated with or without an absolute stationary space, It allowed for the investigations of the contraction hypothesis without diverging into the nature or non-nature of the ether. So what was Einstein's position on the hypothesized ether? Let's hear it from him.
In fact, although skeptics often point to Einstein's theory of relativity, it was Einstein who in 1920 said,
"There are weighty arguments to be adduced in favor of the ether hypothesis. To deny the ether is ultimately to assume that empty space has no physical qualities whatsoever. The fundamental facts of mechanics do not harmonize with this view. According to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable."
So the question remaining with us, when the fundamental flaw of the Michelson and Morley experimental model is exposed, is this. Is there an actual ether or fabric of space as expressed by Albert Einstein? Applying formal logic to the E in the equation E equals mc squared shows that both energy and matter must exist in the universe. Not because the m represents matter, as in fact it actually represents mass, which is not the same as matter, but because of the presence of the E in the equation at all. We know matter exists in the universe because we can see and feel it. Energy, however, by its very nature, eludes our direct observation, and we only know of its existence indirectly. First, by its indirect observance through its effect on matter, and second, by deducing that it must exist if E equals mc squared is true. This is because the first law of thermodynamics states energy can be neither created nor destroyed, only changed in form. So if energy exists, then it must be present around us. While the Michelson and Morley experiment had been designed around a fatal flaw, which had gone unnoticed by three other significant theorists of the late 19th century, Oliver Heaviside, George Fitzgerald, and Hendrik Lorentz, it was Fitzgerald who would later amplify the flawed conclusions of Michelson and Morley by his conjecture of the contraction of matter moving at high speeds, similar to Heaviside's distortion of electrical charge moving through the ether. We now know this as the Fitzgerald-Lorentz contraction hypothesis. To more easily recognize and fully understand the nature of the fatal flaw in measuring the speed of light under various frames of reference, in this section we need to review some basic principles of light. First, we will establish definitions for energy, matter, and force. We will demonstrate the only ways light can be viewed and from what angles. We explore the legitimacy of light being both a wave and a particle. And finally, we show how the nature of light affects both its actual and apparent speed to various stationary and moving observers. For the purposes of presenting the ocean-universe theory, the definitions of energy, matter, and force need to be modified to fit their observed characteristics. For centuries these have been thought of in separate terms, but here they are defined in relation to each other. Mass, which is another aspect, will be explained in the following section when we discuss mass in the context of gravity. For the purposes of the ocean-universe theory, we can think of energy existing in two different states. Per E equals mc squared in the first law of thermodynamics, we must conclude that energy exists within the universe as some element of the universe. Individual units or particles of energy are many times smaller than electrons, and like a fluid move easily through the vast space between the particles of an atom. Matter consist of collections of solidified units of energy, the smallest pieces of which are still much larger than a single unit of energy that composes it. This is the solid state of energy. Force is the resistance energy exerts when it is being displaced by matter or even itself. It can be thought of as the pressure of energy. As we go through this presentation, we need to think in terms of potential and kinetic force rather than potential and kinetic energy. When we think of a wave, we must think of a medium, because a wave by definition is an oscillation occurring amongst the individual particles that make up a medium, such as water or air or the fabric of space. Waves have certain properties that are consistent to the medium they are propagating through. For example, under a given set of conditions of the medium, a wave propagating through it will travel at a constant speed. In the following video, we will see how waves are formed using high-speed photography.
Astonishing. Water doesn't do what we think it does. When you pour water into water, the last droplets do a very quick but amazing dance. It's invisible in human time, but we can see it here. Scientists call this phenomenon the coalescence cascade.
You take
Exactly half of the droplet disappears into the water underneath. The other half becomes a smaller droplet that shoots back into the air.
and then it dumps. We've seen as many as 7 such events in a coalescence cascade.
The water droplet acts a lot like a bouncing ball.
In the video you just saw, you could see a wave being formed, the resistance to it being formed, and the rebound effect, referred to as the coalescent cascade. While these waves were surface waves found at the surface or boundary layer of a medium, rather than pressure waves found within a medium, they are very useful in demonstrating the principles of wave actions. In the next video, we will look at the wave characteristics such as fixed length or duration, propagation as a property of the medium, and we will see how wave speed through the medium is completely independent of the source of the disturbance or the observer. What we're seeing here is a wave being created in a medium. This medium is water. The finger is disturbing the water and the wave is created at that point. But notice that the wave is a property of the medium, not of the finger. The wave isn't attached to the finger. Moving the finger does not influence the wave at all. Once it's created in the medium, it's completely a property of that medium. As the individual moves their finger back and forth and creates multiple waves, you can see that each wave originates at a certain point in the medium and propagates out at a constant speed from that point. You also notice that the waves can overlap and can then continue on after they've crossed each other, each wave continually moving at its own specific speed. In the previous video we saw waves in action. Here we have some still frames of those waves. In the upper left photo we can see a single wave propagation occurring. The red line indicates the wave duration or length of the wave. This property is a property of the medium, not the speed or movement of the disturbing body. In the lower right photo we see multiple waves caused as the disturbing body was moving horizontally relative to the water. There are 3 successive waves that travel together, thus creating a wave duration that is indicated by the red line. When we are speaking of light, we call this duration the length of the beam. And as we will see later, all light beams have a finite beginning and finite ending. A light beam of 1 second in duration would be approximately 300,000 kilometers long. because waves exhibit a constant speed in their medium, we can speak of their length in either units of time or units of length interchangeably. We can also see that when we have waves originating at multiple points along a path of disturbances, the waves will have points of intersection. This is called interference, and this interaction of two waves results in some of the phenomena of light we are familiar with. One of the difficulties in experimenting with light, besides its incredibly fast speed, is the inability to see light from the side. Unlike a speeding train or bullet, light cannot be seen from the side. It can only be seen when it directly hits your eye or some electromechanical sensor. In the series of photos on the left is a laser beam being fired across a vacuum. The top photo shows what you would see if you were looking at the origin from a slight angle. The glowing fuzzy dot results from light reflecting on the sides of the hole as the laser passes through. Seen head-on, the laser would again look like a fuzzy dot just before it put your eye out. And if you were to look at the laser hitting its target, you would again see a fuzzy dot because of the reflection of the wavefront off the target. You would not be able to see the laser light going past you, however. In the series of photos on the right, we have the same laser being fired through an atmosphere of air. In the top photo, you can see the light being reflected off molecules and dust particles all along its path. This light that you can see never reaches the target because it is traveling perpendicular to the light of the laser beam, and it has been absorbed by your eye. In the second photo, you can see not only the fuzzy dot where the laser comes through the whole wall, but also the multitude of reflected paths that the reflected light is taking. Any experiment that would require an observer to see light traveling in a vacuum from the side would be impossible, and such design of an experiment would be invalid. Let's review what we know about light so far. Light originates from an electromagnetic disturbance and is a wave action. Light travels in straight lines from point to point, just as a wave in water or a wave action along a string. The appearance of light bending would be caused by a series of infinitesimally small reflections between two successive points. Light beams are of fixed length. They have a beginning and end, and their length is equal to the duration of the repetitive disturbances in the energy medium. You cannot see or detect light approaching you. It can only be detected once it strikes your eye or other detector. Light, like all wave functions, requires a medium to propagate in. All waves propagate in mediums made up of individual particles, and when these particles are observed individually, they can appear to act independently, as if striking a target from a distance. This is actually a result of the wave propagation motion imparted on them, acting over a short distance. Light propagates through the energy medium, what is often referred to as the fabric of space, or ether, the particles of which are regularly referred to as photons. Even as little as 10 years ago, the direct experimental verification and evidence for the properties of light, as described in the ocean universe theory, would not have been technically feasible. Recently, experiments in ultra-high-speed photography, called femtophotography, which films at 1 trillion frames a second, was able to capture a beam of light, only 1/trillionth of a second in duration, or about 1 millimeter long, as it went through a special reflective atmosphere in a plastic bottle filled with water. Slowing down light 1 billion times was not possible in Michelson's and Morley's time, nor was digital imaging and processing, which may have made a big difference in the conclusions they and others reached on light, energy, and ether. In the following video, we will see the results of this femtophotography, as it gives us our first ever look of a light beam moving through space-time.
Now, if I take a laser pointer and turn it on and off in 1/1,000,000th of a second, which is several femtoseconds, I'll create a packet of photons barely a millimeter wide. And that packet of photons, that bullet, will travel at a speed of light, and again, 1,000,000 times faster than an ordinary bullet. Now, if you take that bullet and take this packet of photons and fire into this bottle, how will those photons shatter into this bottle? How does light look in slow motion? Now, the whole event Now remember, the whole event is effectively taking place in less than a nanosecond. That's how much time it takes for light to travel. But I'm slowing down in this video by a factor of 10 billion so you can see the light in motion.
As we just saw in the video, light moves through space like any other wave propagation, and because it is this propagation or wave action of the energy particles that activates your eye or electromagnetic detector, you cannot see or detect the oncoming light until it actually reaches you. Unlike a bullet or rocket, which you can send a light wave out to, bounce it off the object, and have it return to your eye before the object can hardly move, light cannot be used to detect light. If you were to send a light beam out to reflect off an incoming light beam, as with, say, the case of a rocket, the reflected light would reach your eye at the same time as the original beam. This is because they would both be traveling from the point of impact with each other back to your eye at the exact same speed. The fatal flaw in the Michelson and Morley line of experiments is that they attempt to use the oncoming beam of light to directly measure the speed of the oncoming beam. As you cannot detect the oncoming beam until it reaches your eye, you cannot directly measure the true relative velocity. This is because at the point of impact with the eye, the light has always taken the precise time units to travel the distance it traveled. As we cited earlier, time units and length units are interchangeable measures when speaking of light. So you have effectively divided 1 by 1. In other words, the distance traveled by the light prior to it being detected by the observer is the only distance being considered, as prior to that, the observer didn't know the light existed. In the graphic, we see a light source and a moving observer headed directly at the light source. As the observer and the light beam converge on each other, we can see that while the distance between them is closing at a speed greater than that of light, the observer would not have any reference to the oncoming light. At t equals 0, the distance between the light source and the moving observer traveling at a constant velocity of 1/6 the speed of light is 1 second or 300,000 kilometers. At t equals 2/6 of a second, the distance between the two would be 3/6 of a second or 150,000 kilometers of separation, or 50,000 kilometers closer than a closing rate of 300,000 kilometers per second would account for. The same closing rate is maintained up until t equals 4/6 of a second, at which time the observer and the light beam make their first contact. If you were to measure the distance from the light source to the point of impact, it will always be exactly the speed of light multiplied by the time it took the light to get to that point. Divide this out by time, and you get the speed of light. It appears to be a constant limiting speed, but it isn't. Remember, we said earlier that it has been mathematically established that light movements can be stated as units of time or units of distance, and that the two are interchangeable. Thus our graphic shows at 4/6 of a second and 250,000 kilometers are equally correct ways of stating how far the light traveled before it and the observer collided. In the graphic shown here, we see that the observer is stationary, but the source of the electromagnetic disturbance, i.e. the light, is moving towards the observer. A disturbance in the energy or fabric of space is first made when the rocket is 1 light second, or about 300,000 kilometers from the target. The wave front departs from that point in space-time and starts its journey towards the target. The light is not an aspect of the rocket. It is a wave that propagates out from the point in space-time where it was created, just as the water waves we saw in the earlier video. At time equals 3/3 of a second, the light wave is first striking the observer, and the rocket is 3/6 of a light second, or about 150,000 kilometers from the observer. At this point, the disturbance mechanism is shut off. At 4/3 of a second, there is still light shining on the target, and it will shine for about 1/6 of a second more. At 5/3 of a second, the observer sees no more light, and the last indication of where the rocket was showed that the rocket to be 150,000 kilometers away, when in fact the rocket is actually about 75,000 kilometers from the observer. Light, like a water wave, originates on a point on the fabric of space, or ether, just as we saw earlier. Movement of the source of disturbance in the energy, a flashlight or laser, does not affect the speed at which the light wave travels. Just as we saw earlier, the experimenter's finger had no effect on how fast the water wave traveled. What if an object like a spaceship, or debris and plasma from a cosmic explosion, were to travel at a speed greater than that of light? Exactly what would an observer looking for see? In the following animation, we will see how an object traveling faster than the speed of light would be viewed by a stationary observer. A spacecraft will transverse from left to right. Our observers will be looking through the binoculars as shown to observe the movements of the spacecraft. Let's run this animation one more time. Notice that both observers see the spaceship departing from them, and neither observer sees the spaceship coming towards them. The reason both observers only see the spaceship going away from them is because if the approaching object is traveling faster than the speed of light, it will always be in front of the light waves it is creating. As its closest point to the observer, it will cause a disturbance in the energy or fabric of space, and that light wave front will reach the observer first. The second wave front will be the one caused just before that, and so on, and so on. So in the first wave front created by the spaceship at its farthest distance to the observer will be the last one to arrive at the observer. As the light waves are arriving in reverse order, it will appear as if the ship is moving away rather than moving towards the observer. Consequently, as the ship speeds by, the light wave created at the closest point will arrive first, but the ship will have moved away faster than the light wave was moving towards the observer. Thus the light waves, as they arrive, will make it seem that the ship is moving away from the observer at a rate of speed faster than was observed when it was approaching. When it comes to light, what you can't see, you cannot measure. We can only measure that light which we see, and we see the light we use to measure it with. Thus the distance between the point of the energy disturbance and the point first observed is always the distance that light can travel in units of light time. The distance between point of disturbance to point of detection and speed times time are always equal. Remember, light is a wave motion. It's traveling in a medium, and it's part of the medium. It's not attached to or part of the mechanism that causes the wave disturbance to begin with in the medium.